This is question number 1 from the 4-question practice assignment dealing with combination series parallel circuits. You've been given a circuit and have been asked to solve for 2 ammeters, A1 and A2. The circuit consists of 4 resistors. One of them here is in series with this parallel array. R3 and R4 are in series with each other, but they're in parallel with R2. So the very first part of identifying a question like this is to recognize which portions of the circuit are series and which portions of the circuit are in parallel. And clearly we can see that this is in parallel over here, and we're basically going to solve for this equivalent resistance. I'm going to go ahead and draw this fictitious resistor in here in green, and I'm going to call that R sub EQ. So there's our equivalent resistance, and we need to solve for that. We're going to use the equation for resistors in parallel. So step number 1 is going to be to find the equivalent resistance of the parallel portion of the circuit. We're going to use the form for equivalent resistance. 1 over the equivalent resistance is equal to 1 over R2 in this case, plus 1 over the other parallel leg, which is the sum of R3 plus R4. Okay, so what we get here is 1 over R2, which we know is 2 ohms. That's 1 over 2 ohms, plus 1 over R3 plus R4 is going to be 1 over 8 ohms. And that's not my answer, that's the inverse of my answer. So now what I need to do is find a least common denominator. That's going to be 4/8 plus 1/8, and that's going to give me 5/8. Again, that's not my answer. So I can now draw the conclusion by cross multiplying that the equivalent resistance for this parallel portion of the circuit is 8/5 of an ohm. Or I can say that the equivalent resistance, if I run that through my calculator, is 1.6 ohms. Keep in mind that we're basically treating everything over here as one single resistor, and we've called it the equivalent resistance, and it has a value of 1.6 ohms. That's just kind of one way of conceptualizing this. Okay, the next step then will be to find the total resistance in the circuit. So step number 2, which I'll do here in blue, find the total resistance. The total resistance in the circuit is going to be the sum of R1 plus the equivalent resistance that I've previously found. Now I've taken into account with this equivalent resistance R2, R3, and R4, so by adding that to R1, which is in series with that equivalent resistance, I'll now have taken into account all of the resistive components in the circuit. R1 is 4 ohms, so adding that to 1.6 gives me 5.6 ohms. Step number 3 will be to solve for the total current in the circuit. And the reason that I'm going to take that next step is often I need it to kind of move forward in the problem. But specifically, I'm being asked to solve for the current right here in ammeter number 1. And I'll go ahead and take a minute here to kind of illustrate what's happening in the circuit. I've got a total current leaving the circuit. It then divides into 2 branch currents. One of the branch currents goes through this kind of upper branch, or outer branch, if you will, through R3 and R4, and then back here to this secondary node. And then there's a separate branch current which flows right here through ammeter number 2. It reconvenes with the other branch current right there at the secondary node, and then it reforms my main branch current here, my main current flowing out of the battery, and completes the circuit right here through the battery. So basically what I can say is that I have a total system current at all of these points. This is total current everywhere ahead of that first node, and everywhere after that second node I also have total current. So that's the current leaving the battery here, and I'm looking for it because that's the current flowing through A1. It's also the current flowing through R1 and all the subsequent portions of the wiring here returning to the battery. So let's go ahead and do that. I'm going to use Ohm's law, And I'm going to use Ohm's law globally across the entire circuit. Ohm's law is scalable. I can use it for an individual component or for a portion of the circuit or for the entire circuit. Ohm's law is V is equal to I times R. I'm going to add my subscripts to remind myself that I'm talking about the total circuit. So I've used the subscript T, and so solving for the total current I get V over R is equal to I. Plugging these numbers in, my total voltage is 12 volts. That was given to me in the problem, so I get 12 volts over a total resistance of 5.6 ohms. When I run that through my calculator, that gives me 2.14 amps. Okay, so that's an important number. It's an important number because that's actually my answer to ammeter number 1, 2.14 amps. Ammeter number 1 is here where I have the total system current leaving the battery, and so I know that that's going to be 2.14 amps. Okay, so I'm not done yet. I still have an unknown, and the unknown is here at ammeter number 2. Now, I can use Ohm's law locally at the component level. So if I knew the voltage drop across resistor number 2, if I were to write out Ohm's law here, V equals IR, and I use the subscripts 2 to remind myself that, hey, I'm talking about that particular resistor. If I knew this voltage drop right here across resistor number 2, if I knew the difference in potential in front and behind that resistor, since I know the resistance value, I could easily solve for I. But I don't know it yet, so I need to find another way to figure it out, and that's going to involve using the loop law. The law of loops in this case says that the sum of the voltages lost and gained in any circuit loop is equal to 0, and I know that I gain 12 volts here at the battery. So imagine that I draw a loop, and let's follow this purple line here. This is, although this is a current path, one of the current paths, this is just an arbitrary loop through the circuit. I've selected this one because it passes through R2. So the sum of the voltages lost and gained in that loop has to be 0. Remember, I like to use the analogy of a loop hike here. So if I start here at point P and I'm considering myself at ground level, then I gain 12 volts when I move across the battery. And that means that I have to lose 12 volts between R1, which is right here, and R2. The sum of the voltage drops across R1 and R2 need to add up to 12, so that when I return back here to point P, I'm back to a potential of 0. So I'm using Kirchhoff's law of loops here, and I need to use Ohm's law at resistor 1 in order to find the voltage dropped across it. So let me go ahead and write that out. V1 is equal to I1 times R1. I know I and R. I is the 2.14 amps. That's the total system current flowing through the battery. So 2.14 amps times my R value for 1, which is 4 ohms. And that's going to give me the voltage drop across resistor number 1. This gives me 8.56 volts. So now I know the voltage drop here across resistor number 1, it's negative 8.56 volts. The only reason I'm calling it a negative value is because it's a drop. That means that this side is higher than that side. I have to lose a total of 12 volts between R1 and R6. So now that allows me to figure out what the voltage drop is going to be across R6. So let's move down the paper. Give myself a little bit more room. Okay, so step number 4, give the document a second here to head down. Okay, step number 4 is going to be to use the law of loops. And the law of loops says that the sum of the voltages lost and gained in any circuit loop is going to be equal to 0. So therefore, I can say that the voltage of the battery, which is the 12 volts that I gained, minus V1 minus V2 has to be equal to 0. So since I'm solving for V2, the voltage drop across resistor 2, it's going to be the voltage of the battery, 12 volts, minus 8.56 volts is equal to V2. And so therefore my unknown voltage is going to be 3.44 volts. This very important voltage is one that I was looking for, and it is the voltage drop across that resistor number 2, that unknown that I was looking for earlier. So the last step then, step number 5, will be to use Ohm's law. But I'm going to use Ohm's law locally at resistor number 2, and so now I can say that V is equal to IR and use the subscripts 2, where V is finally now known. Remember earlier I was looking for it. It's 3.44 volts, and I need to divide it by the resistor value of R2, which is 2 ohms. That's going to give me the current through resistor number 2, and that's going to be 1.72 amps. So now I know that I have 1.72 amps flowing through this resistor, which is what I was looking for, which is also flowing through ammeter number 2.